All right, here we have number 5 from the third review day, which I also believe some version of this type of question was, or I know it was on the mock exam. I think it was number 30, which might have been the last one, but I really don't know. But anyway, it was on the mock exam. It was on your review. This is one of the ones that you looked at, I'm assuming, and just was like, what the hell is that? And this was for good reason. You know, sometimes when you do that, it's because you didn't study. But this time, you could have studied everything we learned, and you would have known this, because this is a subtopic that we did not end up having time to go over. Now, because it is a subtopic of it, like, you know, it's a topic within a topic, and the topic itself is something that's only some of the questions. So this, if it shows up at all, is only going to show up like it did on the mock exam. It's only going to be like maybe one multiple choice question, right? So because of that, now that you see what it is, and you know that, if you want to not watch this video and just say, okay, I see that, and I don't know how to do that, so I'm skipping that question, or not skipping, but guessing on that question, that's fine, honestly, because if you have other things you want to do to study, because we only have so much time left, go and do that, right? But if you want to understand what this is, which it's not that complicated, but you just don't know it yet, but if you want to know it, then you can watch the rest of this video. So, you look at this, you're not really sure. The reason that this might have been confusing is because, let me get a different color here, because of the limit statement, right? It looks like it's supposed to be some type of limit, right? So you would think, you know, we talked about looking at a question and trying to figure out what unit it's from, what it's trying to get you to remember. So you look at it at first, you see this part, and you're like, maybe it's trying to get me to remember something about limits, but then you see this, and you're like, what? Which is, you know, a summation notation, so it's like, that might point in the right direction as to what it is. But once you get down to it, you realize, or you will learn, that this is actually a Riemann sum. All right, and what we call this form of writing it out is actually a sigma notation. So we're going to go down here, right? And so this is called the sigma notation of a Riemann sum, right? And which, obviously, a Riemann sum is an approximation of an integral, which you'll see as I explain what this is. This actually will give you the value of the integral, right? It's not just an approximation. So that's kind of where, you know, we might, maybe when we start a Riemann sums, you're like, well, how is this really going to help? It's just an approximation. But we can use the idea of a Riemann sum in conjunction with the idea of limits to get something that's actually equal to an integral. So that's pretty cool. And so the way we do this is using the sigma notation. So if you would like to screenshot this right now, I would do that. This is the basic for it. Like, this is basically what we, you know, kind of skipped out on. This is what the like first page of your notes would have been if we did this subtopic. So this is the gist, right? Which maybe if you're someone who can look at this and be like, okay, I get it, and then you're good, then you're good. But if you need a little bit of help, I am going to draw a little graph, and I'm going to explain what these different parts of this thing means. All right, so on this stuff, hopefully we remember a little bit. So let's pretend we're taking a Riemann sum. So I'm going to draw my boxes, right? Like this, my little sections. Here, maybe I'll make them a little bit bigger so that I can write some notes in there. Right? So say we're taking the Riemann sum from the point A to point B, right? A is our upper bound, B is our lower bound, which is the same. Like, this A and B is that same A and B that's over here, right? That's typical when we're working with integrals, when we're working calculus. A is an upper bound, B is the lower bound. You know, obviously not always. If the question says something different, it's something different. But in general, when we're looking at formulas like this, that will usually be the case. So let's pretend this is our function f, right? So we have our bounds. We've defined a and b, which are part of the equation. And then let's look at, oh, one thing I want to say though is that you see this bottom part here says I equals 1, and up in the question it says k equals 1, and then here it says this crap, and then up here it says k. Some formulas will use I, some formulas will use k. In the AP, obviously they're using k here. I and k mean the same thing. All right, anyway, so something else we see, just looking at this, so we have the limit statement, which we'll get to in a second. And then something else we see is delta x, right? Delta x is something we've seen in Riemann sums before. Delta x is just the change in x from one side of the rectangle to another. So it's that width of the chunk, basically, right? So that's something that we know already, right? And so if we look at how it's defined in this equation, we have delta x again, right? So this is what we're looking at, right? And then this is just further defining some of the points, these here. So delta x is equal to b minus a over n, which again is something that we have looked at before, right? So say you're taking the Riemann sum of, I can't even think of anything right now. You're taking the Riemann sum from 0 to 12 and you want 4 equal parts, right? And so you want to know, what is my delta x going to be, right? So I'm going to take my lower bound, 12, I'm going to subtract 0, and I'm going to divide. I want 4 equal parts, to divide that by 4. So each part will be 3 units wide, right? Same idea here, right? It's the same exact delta x, right? But the reason why the n is in the limit statement is because if we want the actual value of the integral rather than an approximation, we want exactly what it says here. We want n to approach infinity, meaning we want a infinite amount of chunks, which sounds horrible now to say. But between a and b, right, we want like just a million little different rectangles, right? Because as we add more rectangles, those rectangles get smaller, right? And so that margin of error that comes from that rectangle like going over or under approximation, that gets smaller, right? So we want n to be as big as possible. We want as many rectangles as possible so that they can be as small as possible, right? And so that's why we have this limit statement there. And that's also why, rather than being an approximation, it is the value of the integral, right? And then, so moving on to, and then also, I forgot to mention, so I mentioned the I and the K. The reason why it says I or K equals 1 is because we're using whole numbers, right? And so that the I or the K represents which chunk we're talking about, right? Because we have a summation notation here, so we are adding up a bunch of different chunks. Technically, we're adding up, if n is approaching infinity, we're adding up an infinite amount of chunks. But the I or the K is basically just saying which chunk are we on, and the I or K equals 1 is saying each chunk is going up by 1, right? Okay, so next we have this part right here. The f of x equals x sub I, right? And here we've defined x sub I, right? So it equals a, the initial value, right, plus I delta x. And so what that means is you're taking the initial value, say the initial value is 0, you're adding, let's use the example before we said that delta x was 3. 3 times I equals x of I. And then, so say we were on the 4th chunk, right? So we're going to do times 4, that equals 12, right? And so that's telling us x of I is where are we, right? What value are we at the ith chunk or the kth chunk, meaning if I is 4, what value are we at after we have, after we're at the end of the 4th chunk, right? And so that is going to help us, because if we know what value we are at which chunk, we can plug that back into our original equation, right, to get the original equation times the delta x. And so if you look at this, we really have similar components, right, because you have f of x, and then the change in x is similar to dx. Dx is a change in x, right? So it's hard to explain, but it is like its own version of an integral, right? And then so basically what we can do when we have a question like we have above is decipher which part is which in all of this, right? So let me I'll write it out in some different colors for you here. So obviously we have limit as n equals infinity, like always, and then n k equals 1, right? And then we'll get into the actual parts of it. So, here, let me go back. So we want f of something, right? And that's something inside there. We'll have to figure out what x of k is, right? And then we'll also have to figure out what delta x is, right? So let's figure all this out. Obviously that first part is the same, right? And then let's figure all this out. So in this case, it's pretty easy, right? Because you're multiplying delta x at the end, right? And you have this extra bit being multiplied at the end, right? And then here we have an outside function of something in the middle being squared, right? So we can assume that that is f of whatever, right? The function, basically. And then obviously if this is the function, what's on the inside is going to be x of k. So now that we have x of k, we got to remember, what does x of k equal? Well, x of k equals a plus k delta x. Right, so let's define all of these parts. Right, I'll use, or you know what, you can follow along, right? So obviously you can see, right, we have the 1 here. This is going to be our a, right? And then so that would mean this is going to be k delta x. Well, we already know that delta x is equal to this over here, is equal to 2 over n. So that basically solves it for us already. We know that much, right? Okay, so let's write down what we know. We know a equals 1. We know delta x equals 2 over n, right? But we also know that delta x equals b minus a over n. And if a equals 1, that would mean that b equals 3. All right, and then with this, we know that f of x of k equals all of this squared, right? But if this equals x sub k, that would mean that f of just x equals x squared, right? So now we have a function and we have bounds, which means we can write an integral here. So I'm going to switch just to regular black, and let's write an integral. So integral, our a is 1, our b is 3, and our function is x squared. Then obviously we're going to use dx. So this integral is equal to this statement. All right? And so let's do that here. that would be 1/3 x cubed, reverse power rule, evaluated from 3 to 1, so that would be 9/3 minus 1/3, which equals 8/3. So, where do we have that? We have, 3, oh, I'm sorry, 3 cubed is not 9. 3 cubed is 27. So that would be 26/3, which it looks like they have it in like whatever simplest form, I don't know what you call that. So that would simplify out to 8 2/3, which is answer choice B. There we go. All right, so it's basically this whole stuff is important. That's what's going to help you translate. And then the point is using this. And again, this isn't on a formula sheet, so like you would have to memorize it. So if you don't do it by that time, like just be able to identify that this is that type of question and understand if you know it or if you don't know it. If you don't know it, excuse me, don't waste your time, basically. So what you're doing is you're just finding out basically what a, b, and f of x are, and you're turning it into an integral. All right, so hopefully that helps if you wanted to know this. If you didn't want to know this, hopefully you at least watched a little bit of the video to understand that this is a topic that you don't know. And if you see a question like this, it's not going to be that many questions, and you might just want to guess on it. All right, we got to be smart test takers, even if, I mean, obviously we want to study, but even if we come to something we don't know, there's a way to be smart about it. All right, so hopefully that helped, and you got what you needed out of that. All right.